So, in the last class we saw how adjoint network techniques were useful in determining the aliasing functions in a chopped amplifier. We considered not only sinusoidal modulation for the chopping, we also saw square wave modulation, and the motivation for this was that in practice it is much easier to implement square wave chopping in CMOS, especially because you can simply flip the direction of switches. Then we also saw finite bandwidth effects. Okay. And so, this is the overview of what we did yesterday. Let us take a final example on the use of adjoints, now this time at a more circuit level. We have already seen the switched RC network. This is R, this is a periodically operated switch, and this is a capacitance, and this is Vi and phi 1. Let us assume that it has a duty cycle D, all right. So, this is D times T s, and the whole period is T s, all right. And let us say we are interested in finding, as you can see, this is depending on the value of R and C. If R is 0, of course, this is nothing but a sample and hold. If R is very large, it turns out that this can it's used as a mixer, and where the input is typically close to FST or integer multiples of Fs, right. So, the input is a sinusoidal tone or a narrowband tone signal which resides at around multiples of the frequency at which the switch is opened and closed, and the output therefore, the dominant component of the output will be at DC, right, because you are sampling a sine wave at Fs at roughly the same rate. So, the question therefore is what is H sub minus L of j 2 pi LFS, right. So, this is what we need to find, let us say. So, of course, we can do this the hard way, which is basically say, well, let us do it the hard way. We apply for L is 0, well, it is DC. So, what comment can we make about V out by Vi? Well, if you put DC, the output voltage across the capacitor is 1. So, V out by Vi is 1, and therefore, H 0 of j 2 pi 0 is 1, all right. L equal to 1. So, that therefore, the Vi that you put in is cos e to the j 2 pi Fs times t, and we are interested in the output at DC, and typically if you assume that, let us assume for argument's sake that RC is much larger than Ts by Ts times D, right. So, basically it means that the capacitor is not discharging very much, right, or it is slowly discharging. So, how would we do this? Well, if you put e to the j 2 pi f s times t, what the capacitor is going to do is simply average that part of the cycle, which is between 0 and yeah. So, basically let us if we think of the complex exponential as being there is a cos, there is a sine and there is a cos. Right. So, and this is d times Ts, right, and what the capacitor is doing is essentially averaging that part of the waveform, correct, because it keeps seeing the same over all cycles, and therefore, the only way the DC current through the capacitor can be 0 is if the voltage across the capacitor is the average of that part of the waveform. Now, what is that? What is the average of that part of the waveform? Well, I mean, you can do sine and cos separately, or you can do it together if you keep complex notation. So, this is nothing but e to the j 2 pi f s times t dt. Okay, this dt is the calculus dt and not to be confused with the duty cycle d, and this is the integral 0 to d capital T s, and this has to be averaged over that period only, not the entire period. So, this time over d times T s. So, this is the and if the input frequency is not f s, but L times f s, well, you just integrate e to the j 2 pi L f s times t dt from 0 to dTs, and this is nothing but 1 over dTs times e to the j 2 pi L f s times t divided by j 2 pi L f s, and this is evaluated from 0 to dTs, correct. So, h sub minus L of j 2 pi L f s is given by 1 over dTs times e to the j 2 pi L f s times T s is 1. So, that is simply L times d minus 1 divided by j 2 pi L times f s, which as you can see f s times T s is 1. So, this is nothing but e to the j 2 pi L d minus 1 divided by j 2 pi L d. All right. And sanity check, we have already done this for Ts by 4. Let us say d is 25%, which is 0.25. Then h 0 of course is 1, we knew all that already. H minus 1 of j 2 pi f s is 2 by pi plus j 2 by pi from our, we are averaging this over 1 quarter cycle, right, and h minus 2 of j 2 pi f s was nothing but we are averaging over half a cycle. So, if you average the sine over half a cycle, well, I mean we are sorry, so h minus 2 of j 2 pi into 2 f s, this is j 4 pi f s, right. And what will we get there? The sine will continue to be 2 by pi, the cos will be 0, right. So, that will be simply j 2 by pi. And so, and let us see if this makes sense. So, what we have calculated from our this we have seen earlier. Now, let us see if we calculate this. So, h minus L of j 2 pi L f s is nothing but e to the j d becomes 1/4. So, pi by 2 L minus 1 divided by j 2 pi L times 1/4, which is nothing but, yeah, very good. So, let us see, that is nothing but 2 by pi L times j, that is correct, times e to the j pi L by 2 minus 1. Okay. Fortunately, clearly as L tends to 0, the formula also gives 1, right. L equal to 1, what do we see? This is nothing but 2 by j pi times e to the j pi by 2 minus 1, right. This is nothing but minus, so this is 2 by j pi into j minus 1, right, and that is nothing but 1 plus minus 1 is nothing but j square. I mean right, right. So, this is h minus 1 of j 2 pi f s is nothing but 2 by pi, right, times 1 plus j, which is consistent with our previous thing. Similarly, h minus 2 of j 2 pi f s or j 2 pi times 2 f s is nothing but 2 by pi L times j, right, times L becomes 2, e to the j pi becomes e to the j pi. So, that becomes minus 1 minus 1 hold on, I made a mistake here or what? Oh, sorry, here we made a mistake. Oh, sorry, yeah, this we are fine, yeah. So, this basically is this 2 by 2 pi j times minus 2, minus 2 is nothing but minus 2 j square, 2 goes away. So, times minus 2, which is nothing but j 2 by, all right. So, this is consistent, these two are consistent. Similarly, these two are consistent, and of course, these two are consistent. all right. Okay, so now let us see how we apply the adjoint technique. So, what do we do? What do we need to do? We need to first this is N. So, we need to draw the adjoint network, and what is the adjoint network? Well, the voltage source is gone, right, and the resistor remains as it is. We have to flip the timing of the switch, and then you have a capacitor here, and we are interested in the output frequency, which is DC, right, and we are interested in a voltage transfer function. So, what should we do in the adjoint? So, this is N hat. What should we do as far as the adjoint is concerned? We have to apply a current, and at what frequency?
Like DC current.
You have to apply a DC current of say 1 ampere, right, and what are we going to measure?
We have to find all the harmonics.
Of what?
Like current only.
Current where?
That, through R.
Through R, through the voltage source, which is the same as that through R, right. So, this is I out. So, what we need to do therefore is we have applied a DC current into the output port of the adjoint, and phi 1 hat, by the way, is basically, if this is 0, then this is going to be, it's going to be this is D times Ts, all right. So, this is the advantage, I mean this is the period of this is the phi 1 hat, which is the time reversed switch control waveform, and so again, of course, our assumption is that this RC is much greater than Ts times D. So, the first question that I would like to ask is what must be the average output current? Okay, let me lead. Yeah.
On that period, only that period current is injecting.
This the DC current injecting into the capacitor is there for all time. It is a constant current. It is going on injecting regardless of whether the switch is open or closed, right. So, what comment can you make about the current through the capacitor, average current through the capacitor? Anywhere go to infinity. What comment can we make about the DC current through the capacitor? It must be 0. So, if the average current through the capacitor is 0 on average, so therefore, what comment can you make about the average value of I out?
I out also 0.
If I out is 0,
no sir, average of that one will be 1 only.
So, the current, the 1 ampere current that you injected can only flow through ground through two paths. One is through the capacitor and one is through the resistor, right. The average current through the capacitor is 0. If it was not 0, the voltage across the capacitor would have blown up to infinity, correct, which is of course not possible, and so therefore, there is the average current through the resistor is 0. I mean through the resistor it has to be 1, right. Okay. So, therefore, this means therefore that H 0 of j 2 pi 0 must be must be 1. Understand? All right. Okay. Now, what comment can we make about the waveform? I mean, we need to find the steady state output current waveform and look at its Fourier coefficients, and they will give us the all the strengths of the all the harmonic transfer functions that we want. Okay. Now, if you look at the voltage Vc of t in the adjoint, right, during when the switch is closed, what comment can you make about the voltage? Will it fall or will it rise?
It will fall.
It will fall, right, because the capacitor is getting discharged, right. And let us call the maximum voltage V1 and the minimum voltage V2, right. And when the switch is off, what comment can you make about the capacitor voltage?
It will increase.
From where? At what will it start, and then it,
From V2,
yeah, it will start at V2, because remember it is in steady state. So, the voltage across the capacitor is also periodic, and therefore, it will start at V2 and reach V1, correct. Now, what comment can we make about the average value of V1 and V2?
that has to average value is 0. Like D.
Okay, let me ask a leading question. What comment can you therefore make about the current through R? If this is the voltage waveform across the capacitor, what comment can you make about the current through R? The current through R is non-zero only when the switch is on. Yes, correct. So, during this period, the current I out will be 0, correct. All right. Okay. So, when the switch is closed, what comment can you make about the current through R? It will decrease, but what is it? We know the voltage waveform across the capacitor. V1 by R to V2 by R. All right. Okay. And what comment can you make about if you go on increasing the value of the capacitance, what will change in this waveform?
That change V1 by R to V2 by R will be almost like flat on.
Yeah. So, basically if the capacitance becomes larger and larger, well, the voltage V1 and V2 will come closer and closer to each other. Okay. And this is D times Ts, right. So, what comment can you make about the average current? We know that the average current flowing through the output is actually 1. So, what comment can we make about the average value of V1 and V2?
The average current of V1.
What comment can we make about the average value of V1 and V2?
1 by DTS.
Yeah. So, basically V1 by R plus V2 by R, right, divided by 1 by DTS, times the average current is basically the pulse width, the average value of V1 and V2 divided by R, right, times DTS divided by Ts, right, must be equal to 1. Does it make sense? Right? And as the RC time constant becomes larger and larger, what happens is that, so this C keeps increasing, correct. As the capacitance keeps increasing, V1 and V2 become closer and closer to each other, and therefore, in the limit that RC is much larger than Ts, right, V1 is approximately equal to V2, right, and therefore, which is roughly in which case this will be the V average. V average is nothing but 1 ampere times R by D, right. So, this is 1 ampere. So, this is 1 ampere times R by D. So, this is still dimensionally consistent. Okay. So, if you look at the, but we are actually interested in the current waveform. So, the current waveform basically in steady state will therefore be, will look like this, and if R is much larger than D, I mean sorry, if R is if the RC time constant is very, very large, then this current waveform will be for all practical purposes a square wave, I mean a rectangular pulse, right. And what is the height of the rectangular pulse? It simply be 1 by D, correct. The average voltage is 1 R divided by D. The average current will therefore be this divided by, I mean the current waveform will be this. So, to find the H sub minus L of j 2 pi times LFS, what would we need to do? We just have to find the Fourier series of this waveform, right. And how do you find the Fourier series? We know the Fourier transform of a rectangular pulse, right. We just sample the Fourier transform at L times Fs, correct. So, the rectangular pulse starts, so you can see that you can think of this as a rectangular pulse with a delay of, this is 0 and this is Ts, right. There is another pulse just before 0, right, because it is a periodic waveform. So, you can think of it as a rectangular pulse which is centered at 0, but then moved to the left by Ts by 8, because I mean not Ts by 8, Ts by 2D, that is that distance there, right. The width of the pulse is Ts by D, right, and we moved it to the left by DTS by 2. All right, and therefore, so we first find the Fourier transform of the rectangular pulse, move to the left by dTs by 2, and then sample do 1 over Ts of that and sample it at multiples of. So, the rectangular pulse the height is d 1 over d, the width is dTs. So, A T sync F times dTs, right. And what comment can you make about the Fourier series? And then we have to move it to the left by dTs by 2. So, this is multiplied by e to the j 2 pi f times dTs over 2. This is the Fourier transform of the rectangular pulse, and this you multiply by, I mean this you have to sample, you have to multiply by, so the A sub L of this guy is nothing but 1 over Ts. So, this is the nothing but the Fourier transform of the rectangular pulse, and this is sampled at, needs to be sampled at L times Fs, okay. And therefore, this is nothing but sync d times L times e to the j pi times L times d, correct. 2 2 goes away, f becomes L times Fs, Fs times Ts is 1. So, L times T, right. So, A the Fourier expansion is nothing but A sub L is basically right, and so H minus L of 2 pi j 2 pi L F S is simply you basically we know that this is nothing but A, right. So, if you put L equal to minus 1, what do you get? So, H 0 of course is sinc 0 times e to the j 2 pi L times 0, which is 1. That fortunately that works out. H sub 0 of j 2 pi 0 is sinc 0 times the j pi 0, which is 1, all right. And so, we can verify with d equal to quarter, right. So, that is nothing but H sub minus L of j 2 pi times L F S is nothing but sinc. So, sorry, is nothing but sinc L by 4 e to the j pi L by 4. So, L equal to 1. So, you have sin pi by 4 divided by pi by 4, that is the sinc, times cos pi by 4 plus j sin pi by 4, which is 1 by root 2 plus by root 2, right, which is therefore nothing but 2 by pi plus j 2 by pi, right, and that is consistent with what we have we've gotten with, right, and so on and so forth, right. You can verify that the other relations also hold. Okay. So, that it shows another example where we use the concept of adjoint to be able to, in this case actually the circuit was straightforward enough that we could get the answer with the regular method. Also, if you think about it, in our regular expression, since the circuit was simple, we have done the analysis for multiple frequencies at the same time by just doing the math, right. But otherwise, typically you will need multiple input frequencies and then find out the output. All right. So, the adjoint, basically all that you need to do is you just apply the output frequency and then look for the Fourier series of the input, and that basically gives you the Harmonic transfer functions in one shot. Okay.